Electric appliances convert electricity into heat energy, providing you energy in a form that you can use. In this lesson, you will learn how electrical energy transforms into heat energy. At the end of this lesson, you will be able to describe the heating effect of electricity, identify the cause of the heating effect of electricity, illustrate the working of an electric fuse, state and derive Jules' law. When you switch on a bulb, the thin metallic wire or filament in the bulb turns red and the bulb starts glowing. This is because when an electric current passes through a metallic conductor, the conductor gets heated. Thus, electrical energy is transformed into heat energy. This is called the heating effect of electricity. Many appliances in our household utilize the heating effect of electricity. Some common examples are electric irons, room heaters, and storage water heaters. How does the electrical energy of current get converted into heat energy? Every conductor offers resistance to the flow of current. When a potential difference is applied across the ends of a conductor, the free electrons in the conductor start drifting from the low potential end to the high potential end. These electrons collide with the positive ions. That is, the atoms that have lost their electrons. When the collisions take place, the energy of the electrons is transferred to the positive ions, making the ions vibrate more violently. This creates resistance to the flow of electrons. The electric current has to overcome this resistance. The work done by electric current in overcoming this resistance is converted into heat energy. This is the heat that you use in your electrical appliances. Metallic conductors used in electrical heating appliances to convert electrical energy into heat are called heating elements. For example, the filament in a bulb is a heating element. A good heating element should have high resistivity so that it gets heated quickly, high melting point to enable it to withstand high temperature, negligible variation in resistance due to temperature changes. Three metal alloys most commonly used as heating elements are nichrome, an alloy composed of 80% nickel and 20% chromium; manganese, which is 86% copper, 12% manganese, and 2% nickel; constantan, a copper-nickel alloy with 60% copper and 40% nickel. If your electrical appliances receive very weak or very strong current, they could be damaged and stop functioning. To prevent such damage from fluctuations in the current, an electric fuse is used in the circuits of most houses these days. An electric fuse is a safety device used to protect an electric circuit against excessive current. The mechanism of the electric fuse is based on the heating effect of electricity. You may have often heard people talking about replacing the fuse in their homes because the fuse blew, cutting off the power supply. An electric fuse contains a fuse wire that is designed to withstand a particular amount of electricity flowing through it. When the electric supply fluctuates and the current becomes too strong for the wire, it melts and breaks the supply of electricity. Electric fuses are rated according to the current that they can withstand. For example, a fuse rated 5 ampere can withstand current flow to the maximum of 5 ampere. If the current flowing through that circuit exceeds 5 ampere, the fuse wire melts from the heat, cutting off the power supply through that circuit. We can monitor and control the heat generated by electric current by regulating the current supplied to an appliance. James Prescott Joule, a British physicist, expressed the relationship between the heat generated in a conductor and the amount of current flowing through it. This relationship is popularly known as Jules Law or Joule effect. Jules Law states that the amount of heat produced in a conductor is equal to the product of the amount of current squared, the resistance of the conductor, the time for which the current passes through the conductor. To derive Joule's law, let a potential difference of V volts drive a charge Q coulomb through a heating element, and W be the work done. The potential difference is a measure of work done in moving a unit charge across a circuit. From this, we get equation 1. V is equal to W divided by Q, or W is equal to VQ. The amount of electric current passing through a circuit is the product of the rate of electric current and the time of flow. From this, we get equation 2. I is equal to Q divided by T, or Q is equal to IT. Substituting the value of Q in equation 1, we get equation 3. W is equal to VIT. Now let's use Ohm's law. V is equal to IR. In expression 3, to get the formula for the total work done by electric current. The total work done by electric current, W, is equal to I square RT. This work done by electric current to overcome the resistance of a conductor is converted into heat energy, which is represented by H. Hence, H is equal to I square RT. You have learnt in earlier classes that power is the rate of work done, as energy is the capacity to do work. Energy and work are equivalent. Hence, we also define power as the rate of consumption of energy. In terms of electricity, the rate of consumption of electricity is electric power. When an electric current flows through a conductor, the rate of consumption of electricity by an electric circuit is also the rate of dissipation of electrical energy in the form of heat through the conductor. We have seen earlier that electrical energy is expressed as W is equal to VIT, or W is equal to I square RT. Hence, electric power can be expressed as P is equal to VIT by T. This implies P is equal to VI, or P equals to I square RT by T. This implies P is equal to I square R. Substituting V by R for I in the expression P is equal to I square R, and simplifying, we get electric power equals V square by R. The SI unit of electric power is watt and is denoted by W. 1 watt is the power consumed by a conductor having a potential difference of 1 volt across its ends when the current passing through it is 1 ampere. As watt is a small unit, for commercial purposes, we use a bigger unit, kilowatt. A kilowatt is equal to 1,000 watts. According to the definition of power, energy can be represented as the product of power and time. For commercial purposes, the unit of electric energy is kilowatt-hour, denoted by kWh. Simplifying the expression, 1 kilowatt-hour is equal to 3.6 into 10 power 6 watt-seconds. As 1 joule equals 1 watt-second. 1 kilowatt-hour equals 3.6 into 10 power 6 joule.